So, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And hi everyone. So, if you still remember from the previous class, we learned about parallel algorithm design. So, from the slide 1 to until slide 19, we learn about the last two technique of decomposition, which are maybe selalu salah sebut, exploratory and also speculative. And then if we have a difficulty in using a single decomposition technique, so we can implement mixed decomposition, which is called as the hybrid decomposition, if you still remember. And then after that, we also learn about characteristics of tasks. There are three factors or items in the characteristics of tasks that you need to consider, which are task generation, sizes, and also size of the data associated with the task. So, for today's lesson, we want to look at on how to do a mapping. After we already decompose the task into subtasks, that subtask need to be mapped into several processes. So we want to look what are the techniques that can be used to do the mapping process. So what is a mapping process actually? Okay, so mapping is a matching process where the points of one set are matched against the points of another set. So if we have the task, and then we need to do another process like copy and paste, something like that, and then that one we call as mapping. So once a problem has been decomposed into concurrent tasks, several tasks, so it must be mapped to processes. Okay, so that can be executed on a parallel platform. So when we do mapping, we have to make sure that mapping process tu must minimize the overhead. So what are the overhead that we need to consider to minimize the overhead? So there are two primary overhead, which are communication and also idling. Why communication and idling? In this case, we want to divide the big task into several subtasks or concurrent tasks. So of course, it will affect the communication between one task to another task. So, and also why idling when we deal with concurrent tasks, okay, many tasks. So there is sure several tasks need to wait for another task to be complete or finished. So there is an idling issue there. So minimizing this overhead often represents contradicting objective. So sometimes we need to consider these two overhead ni, then we cannot do so much or to maximize the parallel processing process. Okay, so assigning all work to one processor trivially minimizes combination. End up, we cannot do the concurrent task because of what? We want to minimize the communication and idling. We assign all the subtasks back into one processor. Okay, so that's why it said that one processor trivially minimizes communication at the expense of significant idling. So less concurrent tasks because we want to make sure there is no communication and idling overhead. So this is the diagram that I draw in order for you to picturize how the mapping process is being executed. Okay, so we have one big problem here and then being divided into several subtasks. Then this subtask being mapped into processes. Okay. Alright. So next one, mapping techniques for minimum idling. So to ensure we want to minimize the idle. So how we want to map the tasks into several subtasks. task. So mapping must simultaneously minimize idling. So when we do mapping, we have to make sure we also consider the idling issue and also the load balance. So only just balancing load does not minimize idling. Sometimes when we consider only to balance the load, the data to balance, sometimes we did not consider to minimize the idle. So in this case, if you see at the diagram A and B, so A, actually there are 12 tasks. Okay, these 12 tasks are being divided into several mapping styles. So in this task, it being mapped into 4 processes. In A, okay, if you see in A, process 1 until process 4 got balance of load. Okay, all the 12 tasks being divided into the same load or same data sizes. Okay, so and it is load balance. It is set as load balance and also minimize idling. Why minimize idling? All P1, P2, P3 and P4 only have the same task and then they can execute together at once. Okay. However, in B, it said that it load balance because some of the tasks have the same data size, but it has a idle. Okay. It cannot minimize the idling because of what? During T3 until T6, P1 and P2 got idle issue. Okay. Same goes to P3 and P4. There are some time there is an idle here. Okay, in this case, P4 during the first T0 until T3. Okay, meanwhile, P3 ni it's idle on time 4 and 5 until 6. Okay. So, this is an issue of mapping lah. Sometimes we can get this kind of mapping, which is we can balance the load and also minimize the idle. Sometimes we can get the balance of the load, but we cannot minimize the idle between the task or process. Okay. Next one. So to map the task, okay, and to ensure we can minimize the idle, so there are 2 techniques for mapping. First one is called as static and second one is dynamic. Okay, so what is meant by static mapping? So the tasks are mapped to a process in the early stage. So we know that there is a task or there is a dependent between the tasks. So that one we call as static mapping. So for this work, we must have a good estimate of the size of the task. So let's say we already know the task have 12. So we can balance the load and also from the load balancing, we can also minimize the idle. So in this issue of static mapping, we know at the beginning how many tasks or how much the size of the task need to be mapped. Okay. However, even in this case, the problem may be NP complete. Sometimes you cannot do the mapping in a good way lah. Okay, it has an algorithm issue. Sometimes the algorithm unable to do the mapping, and at the end we cannot execute the parallel processing. So the second technique of mapping, it is called as dynamic mapping. So how does the dynamic mapping being executed? Tasks are mapped to processes at runtime. Of course lah, when we talk about dynamic ni, always dynamic being run during the execution. So in this case, we just assume there is a balance of tasks. So that's why we just do the mapping during the run time. Okay, so this why we implement dynamic mapping may be because tasks are generated at runtime or that their sizes are not known. If we have this kind of case, we don't know how many size of the task need to be processed or executed. So we choose dynamic mapping. Then if you know the size of the task, then you can choose static mapping. Okay, other factors that determine the choice of techniques Okay, sometimes we look at the number of tasks. Sometimes we also look at the size of the data that we want to process. So it is called as size of data associated with a task. Sometimes you also look at the nature of the underlying domain. What kind of problem that we want to solve. Okay, sometimes the problem is really complicated. Use lots of data from many locations. So we need to choose either this static mapping or dynamic mapping, right? Okay, so let's go to the next slide. So, okay, this subtopic is called as schemes for static mapping. So, how we want to plan? Scheme also known as systematic plan. So, when we want to do static mapping, what kind of plan that we want to do or execute? Okay, so there are three types. Mappings based on data partitioning means when we do the mapping, we look at the data, okay, by using data partitioning, or based on the task graph partitioning, we need to do some task graph plan or design. And the third one is hybrid mapping, where we combine these two, data partitioning and also task graph partitioning or other technique of mapping. Okay, so let's look at one by one. Okay, this one is mapping the task based on the data partitioning. So it combine data partitioning with the owner computes rule. If you still remember, we have owner compute rules strategy in the data partition. Okay, so then it choose these two combination to do the mapping into subtasks. So in the example, the simplest data decomposition scheme for dense matrix are 1D block distribution scheme. If you have the task, so you can divide the task into several subtasks by using this kind of partitioning lah. Either row-wise distribution or column-wise distribution. You just divide the task into several tasks. Or in this case, P is represent the process from process 1 until process 7. Okay. Then it's column-wise, okay, like this. Alright. So next one, if we don't want to do by using horizontal or row-wise or column-wise, so we also can do block array distribution scheme. So block distribution scheme can be generalized to higher dimension as well. Means we can implement this kind of technique to the large data set or large problems. Okay, so in this case, if it has one big data, okay, or task, that task can be mapped into block type. Okay, okay, this kind of block lah. Okay, and then or this kind of blocking scheme. Okay, either you do like this, P0 until P7 horizontally, P8 and until P15, or you can do like this, the left one. Okay, so next one, what else do we have in the scheme? Another one, okay, this is an example block array distribution scheme. So for multiplying two dense matrix between A and B, so this matrix can be partitioned at the output using block decomposition. Okay, so how to make sure the load is balanced? Okay, so it said that we give each task the same number of element of C. So we have to make sure the size of the output C tu. Okay, so then we can make sure the processor is being balanced. Okay, the load is balanced. Okay, and then the choice of precise decomposition, either 1D or 2D, is determined by the associated communication overhead. So we will know whether the choice or the selected technique is good or not. Okay, so actually it's being determined by the communication overhead lah, whether it has large communication overhead or small communication overhead. So in general, higher dimension decomposition allows the use of larger number of process. The larger the problem, Okay, the higher dimension decomposition we will get, and also in this case the larger number of processes that we need to consider when we do the mapping. Okay, so this is another example how we do the data sharing in dense matrix multiplication. So let's say we have two matrices A and B. So A and B ni when we do the multiplication, okay, so A multiply with P, so at the P5 processor 5. So we know that okay, in P5 we have the data sharing. Okay. And then another example A and B again, when A multiplied with B in this case, okay, at P5 we know that there is a data sharing happen here. Okay. All right. So next one is cyclic and block cyclic distribution, another techniques for mapping. Okay, if the amount of computation associated with data item varies or different, a block decomposition may lead to significant load imbalance. Okay, it's still with the mapping techniques, but in this case, cyclic and block cyclic. So if we deal with different data item, so maybe our mapping technique or processes might obtain load imbalance, might got overhead. Okay, so usually LU decomposition or Gaussian elimination of dense matrix ni always deals with different kinds of data item. So it can implement cyclic and block cyclic distribution. Okay, so let's look at the example. Okay, ni LU factorization. Okay, between L and U. Okay, this one A is the output. Okay, a decomposition of LU factorization into 14 tasks. Okay, so we want to find out whether in this factorization contain load and balance or not. So if you can see here, there are 14 of A or output lah. Okay, so to get A11 until A33, there are 14 processes. Okay, so this is a 3 by 3 two-dimensional block partitioning of the matrix. If we map all tasks associated with a certain block onto a process in a 9-process assembly, then a significant amount of other time will result. So it want to show that okay, this one is one block of mapping, another one, this is another one, and this one is another one. So these 3 mapping process ni consist of different load imbalance lah. If you can see here at the right side ni, okay, it's not balanced. Okay, so it said also, okay, number 1, computing different blocks of method require different amount of work, such as if we want to get A33 here, we need to get L33 and U33 first. So beside that, you can see to solve or to complete the task of A33, it's required 3 processes in task 9, okay, task 13, and also task 14. Okay, and then on the other hand, sometimes like A11, to complete this task, okay, it only needs one step, which is task number 1. So same goes with the other lah. So that's why it said that this is an example of imbalance of the load. Okay, the processes that being implemented or execute is not balanced between the other mapping process. Okay, so because of this, because of the load and balance, so these sections need to wait for the other section to be completed lah. So that's why it said that maybe an idling might occur. Okay, to wait for another until all the processes or tasks being completed or finished. Okay, all right. Okay, this one is block cyclic distribution. So block cyclic distribution ni is being implemented if we want to reduce the load imbalance and idling. So let's say if other previous technique that we use or select is not good and consist or contain load imbalance and idling, so we might use block cyclic distribution. Okay, variation of the block distribution scheme that can be used to elevate the load imbalance and idling problem. So how we want to implement block cyclic ni? So step one is we need to partition an array into many more blocks than the number of available process. So kena create banyak lah to divide the array into many blocks. So step number 2, all the blocks then are assigned to processes in a round robin manner. So what is mean by round robin ni? Ni ialah scheduling algorithm so that each process gets several non-adjacent block. Dia macam nak make it balance. Okay. So it implement round robin manner. Okay, that one is block cyclic distribution. Untuk apa? To reduce the load imbalance and idling. So far so good ke guys? Anak-anak? Boleh Okay. Right. So macam mana dia buat block cyclic distribution tu? Okay. So macam ni lah cara dia for Gaussian elimination. So you can see here, this one is the active part. Okay. Of the matrix. And then by assigning blocks in a block cyclic fashion, each processor receive blocks from different part of the matrix. So different part of the matrix ada column kat sini, column K and column J, and row I and row K contribute to the active part of the matrix. So dia keep on repeating to make sure there is no imbalance of load and also idling. Okay. Alright, so this is example bila dia active part tadi. Okay, this one part ni dia fokuskan to become this one lah. Okay, this is 1 and 2 dimension of block cyclic distribution among 4 processes. So this process P0 until P8 ni, okay, each of these processes consists of different tasks. Ada yang 1, 2, ada yang 3. So they have a different amount of work. Okay. Alright. So another one. They distribute, okay, a cyclic distribution is a special case in which block size is 1. Ini. Okay, a block distribution is a special case in which block size is NP, where N is the dimension of the matrix and P is the number of the process. Itu yang ni, yang B. Okay, either so if you want to make a block cyclic distribution, you can do this kind of like A. The row of the array are grouped into blocks. Each consists of 2 rows resulting in 8 blocks. So ada yang buat macam ni. Ni by row. This one is by block lah. Okay, they create 16 blocks. Each of size 4 by 4 and map into 2 by 2 grid. Lah you perasan dia ada 2 by 2 grid kat situ in a wrap around fashion. Okay. So all of these are example of block cyclic distribution on how they want to map the tasks into processes. Okay, another way to map the task into processes ni, they use graph partitioning. Okay, so in case of sparse matrix, block decomposition are more complex. Sometimes we cannot deal the map issue tu by using block cyclic distribution. So we need to use another option which is graph partitioning. Okay, consider the problem of multiplying sparse graph tadi with a vector. So the graph of the matrix is a useful indicator of the work. So we can look at the graph, okay, and look at the number of nodes. Then we know how many communication between the nodes, okay, is used. Okay, in this case, we would like to partition the graph so as to assign the equal number offload to each process. So it said that when we partition the data based on graph, so actually it can minimize the age of count of the graph partition or minimize the communication. Okay, so let's look at the example. Okay, so this assume this one is the graph of the leg superior. So they partition the graph tu. You nampak it has a different colors, right? So that one is the partition lah, how it partition the data or the task. So this one it is called as random partitioning. Okay, each of the section, the area consists of different technique. Alright, and then if you look at the bottom one, the partitioning for minimum age cut. So dia macam based on colours. Okay, this age is green, and then this one is red, and so on lah. So that one is by using partitioning. Okay, next one. So mapping based on task partitioning yang graph tadi tu. Okay. Partitioning a given task dependency graph across processes. Dia tengok dekat task dependency graph. We need to create the task dependency graph, then we can do the mapping. So determining an optimal mapping for a general task dependency graph is an NP complete problem. Sometimes we cannot solve this issue of mapping lah, because of we do not know how complex the data it was, the task it was. So sometimes we cannot solve the algorithm. So no efficient solution can be obtained, okay, to do the mapping. So excellent heuristics exist for structured graph. Okay, sometimes we need to try and error. Okay, whether to do the mapping to make sure there is a load balance and to minimize the idling. Okay, so this is an example how we do the mapping in task partitioning. So this is the dependency graph for quick sort issue or problem. So it divided into several mapping, okay, several section. So this one is process 0, 1, 2, 3, and so forth lah. Okay, so this is mapping based on the task partitioning by looking at the task dependency graph. Alright. So another example to mapping a sparse graph. Kalau you tengok kat sini, before it creates the task interaction graph, okay, it map the vector matrix multiplication ni based on section. Okay, it divide into 3, process 0, 1 and 2. Okay, then CO, C1, C2 is the process lah. CO, C1, C2. And then 4, 5, 6, 7, 8 is the task or other processes that are related to the process number 0. And 0, 1, 2, 3 until 11 is related to C1 and so on lah. 0, 4, 5, 6 related to 2. So you can do the partitioning by using this kind of version, or you maybe do the partitioning or mapping by transform the matrix into task interaction graph. Okay, so sometimes when we look at the graph, we know that there is a communication or interaction between which node and which node. Okay, so as you can see here, there is a dotted line here. This is represent the section for the each mapping process. Okay, this one is for process 1. Okay, this section for process 0, and another one is, the last one is for process number 2, yeah, the bottom one, right? Okay, so same goes in this example, 1, 2, 4, 5, 7, 8, 0, 5, 6, 1, 2, 6, 9 is the process, okay, that related to CO or C1 or C2. Okay. All right, next one. Okay. hierarchical mapping, sometimes we cannot do only one mapping techniques. Okay, so we need to mix it. Same goes with hybrid decomposition, right? Okay, so the hybrid or combination of several mappings is called as hierarchical mappings. However, hierarchical mappings we need to do step by step, one by one, at one time. Okay, so for example, task mapping of the binary tree quicksort cannot use a large number of processes because of what? Why we cannot unable to implement single mapping technique? Because of this kind of problem use large number of data or processor. So we need to combine more than one mapping techniques. Okay. So hierarchical mapping techniques, it suggests that at the top level, we use one kind of mapping type and the rest at the next level, okay, we use another types of mapping or partitioning process. Okay, so let's look at the example. Okay. So this is the task, okay, being mapped into several processes and it is used task partitioning P1 until P7. Then at the level number 2, it also use task partitioning lagi from P0, P1. Okay, this is called block. Okay, if I'm not mistaken, block cyclic distribution tu. Okay, and then at the lower level tu, dia change the technique to data partitioning lah. Okay. One, if you still remember, we do the exercise on recursive quicksort. Okay. So this is a example of combination two mapping techniques. Why we need to combine? Because we use large of data, right? Okay. So last one is schemes, not last one lah, second last of subtopic. It is called as schemes for dynamic mapping. Just now we have looked many types of scheme for static mapping. In this case, we want to look at the scheme for dynamic mapping. How to do the mapping for dynamic mapping process. So dynamic mapping also known as dynamic load balancing because of what? Load balancing is the primary motivation for dynamic mapping. So to do the dynamic mapping, there are two types or two ways to implement this, either centralized or distributed. Okay, so how the centralized dynamic mapping is being implemented? So we need to look at the word itself lah, centralized. So if centralized, of course, it has one main point. So the processes are designed as masters or slave. Okay, so when a process runs out of work, it requests the master for more work. So it has one controller to control all the slave, okay, or the processes in this case, or the masters. Okay, so when the number of processes increase, the master may become bottleneck because of what? Needs to control or look at the requests of the slave, how many work that they want. Okay, so to reduce this, a process may pick up a number of tasks. So they define or determine in early stage how many number of tasks that they want to pick up. Okay, so this is called as chunk scheduling. Okay, selecting large chunk sizes may lead to significant load imbalance as well. Yes, so always like this, when we deal with large size of data, maybe it may have load imbalances because we do not know at the beginning how many tasks that we want to map. Okay, a number of schemes have been used to gradually decrease chunk size as the computation progresses. So there are many types of schemes to decrease the issue of load and balance in large chunk size. Okay. So this one is centralized. Okay, this is distributed. distributed. So how does the distributed dynamic mapping being implemented? So each process can send or receive work from other processes. There is no master or slave anymore. So all the process, each of the process can send or receive from other processes. All can be interacted together, being communicate together. So it actually remove the bottleneck in centralized scheme because there is no controller, no one can control the workload. So everyone, all the process can control by themselves lah. They can communicate with each other. So however, we need to consider 4 critical questions. So the first one is how are sensing and receiving processes paired together? The first one lah, let's say we want to do the connection or communicate between 2 processes. So how they are, actually this is not sensing, this is sending. How they want to send and receive the process. Okay, which process that we need to pair up. So who initiate the work transfer? Who will start first? How much work is transferred? So we need to think about this. And when is a transfer triggered? Yes, if we do not have the controller, so all the processes need to consider this kind of question lah to avoid the traffic jam, something like that. So answers to these questions are generally application specific. We will look at some of this technique, okay, nanti. Okay, so there are some complex procedure that we need to consider when we want to implement the dynamic mapping. Okay, what else? Okay, so now we move on to the minimize the interaction overhead. So at earlier slide just now, we discussed about load imbalance and idling, right? So it deals with the interaction actually. So how to minimize the interaction between the processes? The first one, you can do what? To maximize the data locality. So we use locals. Usually in this case catch, okay, to minimize the locality where possible, reuse intermediate data, the data that near to the process. Okay, so restructured computation so that data can be reused in smaller time window. So this is the way number 1 or option number 1 to minimize the interaction. Use data locality. Second one, you can minimize the volume of data exchange. Okay, so when we exchange data between the processes, we might increase the volume. Okay, so to minimize the volume, so because it deals with a cost associated with each word that is communicated, the large the word, the higher the maximize the volume that we want to exchange the data. So we need to consider lah how what are the size of the data that we want to send or receive between the 2 processes. So number 3, to minimize frequency of interaction. So there is an interaction, so we need to minimize it because there is a cost, startup cost when we do the interaction. So sometimes we can try to merge multiple interaction to one. No need to do many interaction. Maybe we can combine it into one interaction only. So step number 4 or option number 4 is to minimize contention and hotspot. Okay, so by using decentralized technique, replicate the data where necessary. Okay, so another option that you may use is by overlapping computation with interaction. We do the overlap. Okay, you either by using non-blocking communication, multi-thread, and pre-fetching to hide the latency. Another way is by replicate the data. So you do the replicate. So any tasks or processes can access the data quickly. Okay. Or other than that, using group communication instead of one individual communication instead of point to point. Or last one, by overlap the interaction with other interaction. If the interaction is similar from the previous one, maybe we can overlap it. Okay, for the latter interaction or process. Okay, so last subtopic, it is called as parallel algorithm model. So if we already considered the mapping process, how we want to use or choose the decomposition technique, okay, if we already decide all of this, so we might choose what kind of model that can be implemented when we want to do the parallel computing. So actually an algorithm model is a way of structuring a parallel algorithm. So why we need to choose the model? So we need to structure on how we want to do the parallel process. So when we have this kind of guideline, so you can know which decomposition technique that you can use, which kind of mapping technique that you might apply. Okay, so then you can apply the appropriate strategy to what? To minimize the interaction lah. To avoid loads imbalance, to avoid the idle. So the first model is called as data parallel model. Okay, it's focused on data. So you might use this kind of model when your tasks are static or semi-static and then map to the process and each task performs similar operation. So you can use this kind of data parallel model. Okay, so for task graph model, starting from task dependency graph, the interrelationship among the tasks are utilized to promote locality or to reduce the interaction cost. If you have large size of data or tasks, so maybe you can use task graph model because of what you can know which node or which task interact between them. Okay, it's because of what? We need to design the graph. Okay, we need to look at the task dependency graph. Okay, that one is task graph model. So another model is called as master-slave model. So in this model, one or more processes generate work and allocate it to worker processes. So this kind of model, you may use either static or dynamic lah. Okay, if you have one or more processes. Okay, so you can use this kind of model, either master or slave. Okay, then another one is called as pipeline or producer consumer model. So a stream of data is passed through a succession of processes, each of which performs some task on it. It's a pipeline. You can stream the data. Okay, through the succession of processes. Okay, and then another model is called as hybrid models. So you can combine more than one model. You can compose either a multiple model applied hierarchically or multiple model applied sequentially to different phases. Means you have different phases, many levels of concurrency or parallel computing. So you can implement the hybrid model. You no need to fix and choosing one model only. So you can hybrid it in certain levels or certain problems that you need to solve. Okay. Okay. I think this is the last slide. Okay. Okay. So this is the last slide. So to conclude, what we have learned today. So basically, there are many types of mapping techniques. Okay, you all, can you define one of the mapping technique that you remember in this lecture? There are many types of mapping technique. One of the mapping techniques that stuck in your mind. What is it? Ada sesiapa nak jawab? Banyak dah ada scroll dah ni. Okay. What is the function Why we need to do the mapping? Why? So we need to do the mapping to minimize the overhead during the parallel processing. That is the main function on mapping process. Okay. So what are the overhead, guys? What are the overhead that might happen during the mapping process? Who can answer? Anyone? Communication and idling. Okay, good. Irfan, communication and idling. Yes, betul. Anyone? Ada lagi? Betul So depan mata je ni Okay, and then what else that we learn? Okay, so this is the example on how to do the load and balance and idling tu Sometimes the question will ask you okay, how to solve this kind of issue. So you need to think lah. Okay, you need to consider how many tasks in one problem and then how you want to make it load balance. To reduce the idling. So you need to do like this. Like that Okay. What else that you learn? Okay, so mapping techniques, there are two types, either static or dynamic. Okay, and then you need to consider the number of tasks during the mapping and then the size of the data itself, the nature of the problem that you want to solve. All those things need to be considered when you do the mapping techniques. Okay, then we look one by one the scheme, how we want to do the mapping. Okay, in this slide, we learn on how the scheme for static and also the scheme for dynamic. So kalau static ada 3 jenis based on data partitioning, task graph and also hybrid. Okay, what else? So let's look at for dynamic. Kalau dynamic ada berapa guys? Ni semua static tau. Okay. Okay, this one. So, there are two types for dynamic mapping, centralized or distributed. Okay, what else that you learn? So, centralized, dia kena ada one controller to control all the processes. If dynamic, okay, if distributed, all the processes can communicate with each other, can interact, but they need to question themselves before they start to do the mapping by determining how to send the data and receive the data, who initiate the work transfer, who start first, okay, who will receive, who will send, okay, and many other questions, okay, to be considered. Okay, lastly, not lastly, second last, we learn several options how to minimize the interaction. So you need to know at least 4 lah to how to minimize the interaction. So we need to consider the locality of the data, the volume of the data, the frequency of the interaction, okay, and then the contention and also the hot spot. If you memorize 4, it's nice, okay. Okay, and then we have other options to minimize the interaction. And last one is to choose what kind of parallel algorithm model when you want to do the mapping. Ingatlah dua. Either data parallel model ke. Okay, sometimes the question will give you a situation. Then it want you to choose which model is suitable to be implemented to this situation. So you have to make sure lah you really understand all the model that being given either data or task graph or master slave model, pipeline or hybrid. Okay. Okay.